Hello, we're now going to look at assembly code both in this video and in the next few videos, where we're going to sort of build up and look at how we can write assembly code programs, which is very, very different from the programming you're probably used to. So it takes a bit of studying to understand how this all works. So let's focus more on what assembly code is in this video before looking at how we can write specific programs in the next few. Assembly code itself, or assembly language, whatever you want to call it, is an example, one of the only two examples of a low-level language. The only other example of low-level language is machine code, whereas a high-level language is something like Python or Java or C++. The difference is the level of abstraction. A low-level language has a low level of abstraction, meaning it's quite similar to what the CPU is actually doing, whereas something like Python is very, very abstracted away. A lot of stuff is just a simplification of what the computer is doing. So assembly code and machine code are quite close to what the CPU is doing, which can make it challenging. The way that assembly code and machine code are linked is through a one-to-one relationship. Now, what that means is assembly code is very, very closely tied to the underlying machine code. What the CPU actually executes is for machine code is just binary, and assembly code is designed to be very, very similar to it, so that each part of an assembly code instruction can be converted by an assembler really easily to machine code, because a computer will never actually directly execute assembly code in the same way that it would never actually execute Python code. It has to get translated to machine code to be executed. The jump from Python code to machine code is quite big, so the compiler or the interpreter has quite a lot of work to do, but the jump from assembly to machine code is very small because it can just sub out the assembly code instruction to the binary. So for example, in the instruction set, LDA might be given the binary number 5 to represent it. So I represent 5 in binary here, and 11 might just be converted to just what 11 is in binary. So quite a simple process, one-to-one. Now, machine code is platform specific because different CPUs and different families of CPUs have got different instruction sets. So because of this one-to-one relationship, if machine code is platform specific, which it is, therefore so is assembly code. So consequently, there isn't just one assembly language, there are loads of different assembly languages for specific CPUs. So you can put in your CV that you know assembly code, but you need to be careful that you don't try and claim you know every assembly language, because obviously you will only potentially know one, maybe. And the one for the OCR exam is actually a made-up assembly language, so be careful putting it on your CV. This is got a slightly weird name, Little Man Computer, which will abbreviate for LMC. It's been around for a very, very long time. It's designed for teaching, because a real assembly language maybe has 80 instructions. LMC has, I think, about 11. And we'll look at those instructions within LMC in the next few videos. But just to sort of prep us for that, let's think about what an instruction is and also the anatomy of an instruction. How can an instruction be broken down further? Well, two key terms you need to be aware of are opcode and operand. So an instruction does something. It adds, it subtracts, it loads, it stores. The opcode is the part of the instruction which represents that. So it's often a word like add or sub for subtract. Now, not every instruction requires an operand. For example, a really simple instruction might be to stop your program. That doesn't need any operand because an operand is data. It's data being used with the instruction. Some things like add will need an operand because we need to know what to add. So it tells us what data we're using in the add operation. Now, LMC only ever uses at most one operand, but real assembly languages often use multiple operands. So that's just something to be aware of. One thing which is confusing about assembly code as we go through the next few videos is the operand is often, not always, but often an address of where the data to be actually used is held in memory. And often that address will be written as a number, but it also can be written as a word, and the word is referred to as a label. So we'll come on to how this works and what this means in future videos in more detail, but just to give us a kind of essence as we introduce it here, something like imp is a simple instruction in Little Man Computer assembly language. Imp is short for input. That is a whole instruction, but it just consists of an opcode, which is telling us to input something. There is no operand required here because the user will type in something. There's no operand. Another example, which is the stopping one I mentioned, this is halting. It stops our program. Again, just consists of an opcode, no operand necessary. However, add will need to have an operand. Here I've put 10 as my operand, and most of the time this isn't referring to the literal value 10. I'm not adding 10 here, I'm adding whatever is located at memory address 10. Now this can change based on the mode of addressing, which we'll cover in a future video, which is why I said often here. It's not always, but for most cases, this is an address, not an actual value. And even more confusingly, here's a different opcode, sta. I could have a word, which is really also representing an address. That is an example of a label. So we'll unpack what this means. For now, we need to know the terms opcode, operand. The opcode is written first, the operand is written second. LMC only ever uses either 0 operands or 1 operand. Let's end by evaluating assembly code. In the real life, nobody is forcing you at gunpoint to learn assembly code. Obviously, you're doing an A-level, so you kind of have to. But why would some people choose to use assembly code? What are some advantages? Well, because it's low level and very close to what the CPU is actually doing, you get a lot more control over the hardware. So you can modify things like registers a lot more easily. You can move stuff around in memory much more easily than you can in a high-level programming language. High-level languages don't really trust you to do stuff like that, whereas assembly code, you can do that. And apart from potentially people just liking more control, the benefits of this are you can, if you know what you're doing, optimize your programs a lot more to make them run faster or take up less memory space. A high-level language will do a lot of work for you. Some of that work might be unnecessary. Some of that adds what's called an overhead, where it is either taking a bit longer than it needs to, or it's taking more memory than it needs to. For example, the compiler might include things which are not necessary to run it. A high-level language might have a built-in function which is not written in the most efficient way, so it takes a little bit longer to execute. Whereas assembly code, you can do all of that yourself, and you're not relying on somebody else's work slowing you down or taking up more space. And in the past, there was quite a big difference in speed and memory use versus high-level languages. However, because compilers have got so efficient, actually this is not quite as dramatic as it used to be, which is why I've said it may be faster, may take up less memory space. Now, machine code has got all of these advantages, but it's just very, very difficult to write. Writing in pure binary is extremely challenging, whereas at least assembly code has some bits of English. It has the unary numbers. It's a little bit more readable compared to machine code, so that's why you might use assembly over machine code. However, compared to high-level languages, the code is definitely less readable. This makes it more challenging to program. Errors are more likely. It can be more confusing to understand, as we'll see. The code is almost always less concise. Even doing quite a simple task like adding up two numbers together could be done in one line. In a high-level language, it might take several. In an assembly code language, it's often just a lot longer to have to do because part of the reason is less tools are available to help you. And a high-level language has loads of built-in subroutines to help you do stuff. It has things like libraries to also help you. Because they're not available, you've got to do all the work yourself, which makes the code longer, but also adds to the challenge. I think that point about it being less concise might seem like it conflicts with the advantage of taking up less memory space. But don't forget that high-level languages have to be translated to machine code. So just because on your screen, the high-level language looks shorter, doesn't mean that actually in binary, it turns out to be shorter than the assembly code equivalent. Because like I say, high-level languages often maybe include things which are not necessary. It might slow it down slightly. The compiler might add some overhead to this process. So when it's converted to machine code, it may be that assembly code is actually a bit more concise. However, for the user and the programmer, high-level languages are usually a lot shorter. And the last big disadvantage of assembly code is because it's platform specific, I can't just take one assembly language program and put it on all computers because different computers have got different CPUs and have got different instruction sets. So a high-level language, that work is dealt with by the interpreter or the compiler. But assembly code, I need to target a particular family of CPUs and it won't work on any other family of CPUs.